Just a minute. Yes. So let's start today's session. So welcome all of you for week 8 um, content of Aspen Plus Simulation Software, a basic course for beginners. So I assume that Sari is currently focusing on case studies, right?
Yes.
So today's session, I have one case study with a train of distillation units, and I have one problem, one reactive distillation unit, and one reactor model. So let's take this problem after some time. This is just repetition. So I will start with LHHW kinetics. So what is the full form of LHHW? LHHW is Langmuir Hinshelwood Eugen Watson model. So that is based on some adsorption, driving force is adsorption. So for this model, rate is given by kinetic factor into driving force divided by adsorption expression, and rate constant K is expressed as that is same expression K into T by T naught raised to N exponent of minus E by R 1 by T minus 1 by T naught. So in last lecture, we solved one RPFR problem. So in that case, we took value of N is equal to 0. So this term just got vanished, and we had k is equal to small k exponent of minus e by r 1 by t minus 1 by t naught. So we can also consider some value of n. So in this case, driving force is given by this following expression K1 into some concentration dependency minus K2 into some concentration dependency, and overall rate constant is given by this term, that is AI plus BI by T plus CI ln T plus DIT. So when we solve this problem, it will be more clear what is this trying to say. So let's take the example of production of ketene. So I will just read out the problem. So in acetic anhydride manufacturing unit, the cracking of acetone produces ketene and methane according to the following irreversible vapor phase reaction. So in this first line, we are told the reaction is irreversible reaction and it is vapor phase reaction. This reaction is first order with respect to acetone. So order of reaction is also given. Pure acetone feed Pure acetone feed with a flow rate of 130 kilomoles per hour enters a plug flow reactor at 725 degrees Celsius and 1.5 atmosphere. So feed condition and reactor conditions are given. The kinetic data is also given. Value of K, activation energy N is equal to 0 is given here, and T0 is given as 980. The unit of pre-exponential factor clearly indicates the CI basis. Then to use the Langmuir LHHW model, set 0 for all coefficients under term 1 and that for all coefficients except A under term 2. Take a very large negative value of coefficient A. And here length of here it is told adiabatic PFR with length and specified diameter. So we are supposed to use some property method and compute the mole fraction of product. So I will show you how to solve this problem. So I guess my screen is visible.
Yes, yes, it is visible.
How many we have joined today? There are 7 students. Okay. So let's start the problem. Okay. Does anyone of you want to take the screenshot of the problem, or you have already done it?
Done already.
Okay. Just take the snapshot, the screenshot of this problem statement, and let me know when I should move ahead. Is this done, Drew?
Yes, sir. I've taken the screenshot, sir.
Okay, so let's move ahead. I will solve this problem. I will show you how to solve it. So first we have three components. Those are I have book with me. So I'm taking that question. I will be reading that problem statement from here only. So we have acetone, ketene, and methane. So let's add these three component acetone. It will show up. Is anyone of you solving with me?
Yes, sir.
I am
Yes,
sorry.
sir.
Okay. My internet is. Just give me a minute. I will just write down acetone here. Acetone. Mm, my Aspen is bit slow right now. Just a minute.
Even mine.
Okay, yes. Acetone, ketene, and methane. Okay. So, oh, it's wrong. It's wrong. It's wrong. It's methane. So we have to write down methane. Okay, so we have added all three components. Now I will press next and we will add property method. So we are supposed to use CISO zero property method. So it's here. Okay. Now I'll press next. So I guess we have all input ready. Now we need to create our flow sheet. So for that, okay, let's go to reactors. We need to add RPFR. So I'm just adding RPFR from here. One inlet stream and one outlet stream. Correct? Okay, I will just use these align blocks to make it straight. Okay, so here we have reactants. I'm writing it as R, and product stream I'm writing it as P. And here I will just rename it as RPFR. So I will now press next. So what is told? The reaction conditions we have 725. What is written? Pure acetone feed with a flow rate of 130 kilomoles per hour enters at 725 degrees Celsius and 1.5 atmospheric pressure. So we have inlet stream as 725 degrees Celsius and 1.5. Yes, it is 1.5 atmospheric pressure with flow rate of 130 kilomoles per hour. And our feed contains pure acetone. So we'll write mole fraction of acetone as 1. Okay, is this clear to everyone?
Which method you are used?
CSOP 0 method, that is ideal method in problem statement to store this thing. If you can see, it is SYSOP0 method. Okay. Dhruv, are you following? You are solving with me?
Yes, sir.
Okay. So we have added feed conditions. Those are 725 degrees Celsius, 1.5 atmospheric pressure, molar flow rate, and mole fraction. Now I will press next. Okay. So in problem here you can see that it is written the sample adiabatic PFR is 3 meter in length and 0.6 meter in diameter. So please read problem statement very carefully. According to that you will choose your reactor condition. So here it will be adiabatic reactor, right? Now we'll go to configuration. So it is 3 meter in length and 0.6 meter in diameter. So 3 meter in length and 0.6 meters in diameter. And one more thing, we were told that it is a vapor phase reaction. So here by default vapor phase is chosen. So if it's not, then you need to change it to some other. If it's told that the reaction is liquid phase, then you have to change from vapor to liquid here. In our case, it is vapor phase reaction. So we'll keep it as vapor phase only. Now I will press next. Okay, so now I need to add a reaction. So to add the reaction from left hand side, we will choose reactions option. We will click here new R1 and we have LHHW kind of model. Okay, this time we will not be choosing power law because in problem statement it is LHHW model. So I will just choose LHHW. I will press OK. Now we need to define our reactions. So one more thing, it is told that the reaction is irreversible reaction. So we have only this one reaction. Acetone gives ketene plus methane. If we are told the reaction is reversible, then we need to add one more reaction that says ketene plus methane gives acetone. But here it is irreversible reaction. So we will add only one reaction. that is acetone giving ketene and methane, and stoichiometric coefficient of acetone will be -1 as it's a reactant, and ketene and methane will have 1. Okay, now we need to provide kinetic data. So here we need to change reacting phase from liquid to vapor. Now we are given value of K is 1.1 second inverse, and value of E exponential factor activation energy, that is 28.5 into 10 raised to 7, sorry, right, E7. Okay, and the unit is what is the unit? Joule per kilomole. So I will just write joule per kilomole, and value of T0 is given to us as 980 Kelvin. So as we are adding the value of T0, we are following this term K, this term that I showed you in my slides, this kind of kinetic factor. Okay, so this done. Now I'll press next. Okay, so here we need to provide term 1 and term 2. So we need to choose driving force. So okay, I will re-show you. Yes, sorry, here driving force will click for term 1. Okay, let's see in what is told in problem statement. So it is told that set 0 for all coefficients under term 1, and that for all coefficients except a under 2. So we are at term 1. So term 1, okay, first let's add exponent. So it is told that the reaction is first order. Here this reaction is first order with respect to acetone. So here we will add acetone exponent as 1 and all this term as 0. Under term, okay, it is already there in term 1 0. Now we will add term 2, and CI basis is also molarity as per question. Now in term 2 it is told that value of first coefficient take very large negative number. See here it's written that take a very large negative value for coefficient a under term 2. So let's take some -1 E6. Okay, and I will just close it. Okay, what more input is left? I guess input is over. Okay, now we need to select this reaction. So I have selected this reaction and I will run my simulation.
Fasil, adsorption reaction is not in this section. There is no adsorption.
No, we'll not. We are adding it under driving force, not under adsorption, because it's a reaction. So for reaction, we will need to add those exponent factor, the basically the order of reaction. I guess that option is not available under adsorption term.
Similar to power law.
Yes, okay. Just give me a
Almost
minute.
same.
I'm sorry, just give me a minute. Just give me a minute. So after simulation, we are getting in feed. We had okay, it's
Sir,
not simulation.
sir, could you show the defining of stoichiometry once again?
Okay, just give me a minute. Yes, it's driving force only. Okay, so here, okay, it's not simulated. We have some issues. So here it's adiabatic reactor with 3 meter length, 0.6 meter diameter, vapor phase. Okay, we need to check our reaction. So here reaction acetone gives ketene plus methane. This is the kinetics, that is vapor
Sir,
phase
yeah, could you,
reaction.
sir, show the stoichiometry?
Uh, Stoichiometry, okay. It is -1
One,
for
one. Okay, sir.
acetone and 1 for methane and ketene. I guess this is correct. Yes, -1 1 1. This is correct. Now, okay, value of K is 1.1. It's in vapor phase. 1.1. Then value of E is 2.85 into 10 raised to 8 joules per kilomole, and T0 is 980 Kelvin. So this is also correct. Now we will choose driving force. This is also fine. Under term 1, we have 1 and everything else has 0. And under term 2, we have 3, 4, 5, 6, and this is correct. And 0. We need to, I guess, write it down here. I don't think it will. -1 into 10 raised to 6. Let's add some more negative number. Let's say 8. Okay. So term 1 and term 2, those are correct. Yes. Now it should work. I'll just press close. I will reset my. Did you guys follow? Temperature is 980 Kelvin. Yes, T0 is 980 Kelvin. This is also correct. Okay, so I will just run this simulation. Just wait for a minute.
Sir, the value of E is 28.5 and yeah, same value. Okay. It auto corrected.
Yes, yes. E will be
Okay.
2.85. Does anyone of you got the results?
Yes,
I
sir.
have got the result.
So just
Not
a
yet.
minute. It's still running. We can give -1 into 10 raised to 6. It was fine actually. Just wait. It's processing. Can any one of you tell me the answers that you are getting if the simulation is over?
Answers of
Answers of
amount of
mole fraction of product, ketene and methane.
we're getting 0.11 in both.
Ketene and methane, yeah, correct. You are correct. 0.11 for both ketene and methane and 0.76 for acetone.
Acetone. Yes.
Yes, who was this Rohit, I guess?
I am
Or
Prakash.
okay, okay, okay. Dhruv, did you get?
No, sir.
Or your
My reaction has not proceeded, sir.
just give me a minute. Let this first complete. Okay, no, it's still taking time. Okay, so can any one of you share your screen and show the results? Mine is taking time actually. That's fine.
You want me to share my screen and show the results?
Yes, please do it. Share your screen and start your video also so we all can see you.
Wait a minute.
Okay, wait, just a minute, just a minute. I have got the results. Just a minute. Streams. No, I'm not getting it actually. I don't know. Okay, yeah, it is 0.7611 for acetone and 0.119 for ketene and methane. So we had 100% acetone and the reaction occurred. So here
Your
we can.
screen is not visible.
Oh, I'm sorry. I'm sorry. I'm sorry. I'm sorry. Sorry. Yeah, now it is visible, right? So here we can see that reactant we had 100% acetone and in product we got 76% acetone and rest equal contribution from ketene and methane. So we need to optimize this, right? We can't proceed with this thing. We have 76% still ethanol acetone in our product stream, right? So we need to
Sir,
play
I
with.
got 54 acetone and 22 ketene and methane.
No, no. Just give me a minute. You will share your
Sure.
screen, show it to everyone. So we need to optimize this reactor, right? We need to play with some parameter to get more amount of ketene and methane in product and less amount of acetone. It means we need to convert more and more amount of acetone into ketene and methane. So we can play with some sensitivity analysis. We can change the length of the reactor. We can play with length and diameter of the reactor and we can play with temperature pressure conditions and we can see what are we observing. So we'll not do this for this time because we have already done this. So okay, Dhruv, can you share your screen and see what was the issue?
Sure, sir.
I hope this problem is clear to everyone.
Sir, is it visible?
Yes, it is visible. You are getting yeah, these are not right conditions. Okay, so I just go to reactor conditions first. You check mole fraction only, right? Okay, it is adiabatic reactor. No, not mass fraction, mole fractions. Okay, those are not matching. Mole fractions are 0.22 and Okay, just go to your reactor. There is some issue with oh, you already performed sensitivity analysis, or it's
No,
just
sir.
length. Okay, you have shown that plot. Okay, it is adiabatic, right? Now go to configurations. It is 3 meter in length and 0.6 meter in diameter and vapor phase. Okay, now go to reaction. I guess it's the issue with reaction. Show me your reaction. Yes, input. -1, 1, 1, correct. Now go to kinetic. I guess there only 1.1 vapor phase. Yeah, now go to driving force. I guess this is there. Okay, here under term one, you need to add that. Okay, what in problem statement we are told that the reaction is first order reaction with respect to acetone. So here you need to add uh, exponent of acetone as 1 under term 1. Yeah. Now
Okay.
close it and run it. Reset your simulation and run. It is taking zero order reaction. That's why you are getting something different.
Yes, sir.
Okay. Go to mole fractions. Yes. Yes, now it's correct. Okay, tell me
Now
one
it's correct.
thing.
Yes, sir.
Okay, can you open problem statement? Okay, just tell me one thing. Let's say you are not told that the reaction is first order with respect to acetone. Then how will you assume that the reaction is first order?
Sir, unit is S-1 of K.
Second inverse. Okay. And how will you assume that it is with respect to acetone, not with respect to product stream?
Sir,
It's irreversible. Okay. So it
yes, sir.
will only proceed
Irreversible.
like acetone gives ketene plus methane. Okay. So I hope this problem is clear to everyone, and whoever other than Dhruv were solving, you got the same answer. Samira, did you get the same thing?
Yes, sir.
Okay. Anyone other than Harshil is also solving, I guess. Okay, so let's move ahead. Okay, I will share my screen.
I'll stop, sir.
Okay, is it visible?
Yes, sir.
Yes, sir.
Okay, so we have I'm giving you option. I have this one problem statement with comparison of plug flow reactor CSTR and this other models R stoic and R gibbs. We have this one problem and we have RD column, reactive distillation column. So first, should we complete reaction part only? Any one of you will share their screen and solve this problem, or should we first move ahead with RD column?
RD column.
Okay, we have RD column and we have one case study of this chain of distillation unit. Okay, so let's move with RD column, and if time permits, any one of you will share your screen and solve this problem. Okay. So let's take this reactive distillation unit. So first take screenshot. I will read out the problem. In a reactive distillation column shown in this figure, the decomposition of HI to H2 and I2 is considered. The column has total 8 stages, including this partial condenser and reboiler, and it operates at 25 bar absolute pressure. Okay, so we are given some feed conditions like temperature is given of feed, pressure, flow rate, and feed stage is given. And component mole fraction, we have amount of water that may be coming out from some upstream unit. So we have combination of HI, hydrogen iodide, H2O, H2 and I2 in our feed stream. So and reflux ratio and D by F ratio is also given. So the HI decomposition reaction is 2 times of HI gives H2 plus I2 is an equilibrium limited reaction taking place in vapor phase. So here you need to focus on this term. It is a vapor phase reaction. The chemical equilibrium constant is given in terms of this. This is equilibrium constant. It will be this only, right? Concentration of H2 I2 divided by concentration of HI raised to 2. And it's in terms of partial pressure, right? It should be in terms of partial pressure. The expression of the HI decomposition chemical equilibrium constant, this expression of ln K is given as minus 0.03684 minus 2772.77 divided by T. And here temperature is in Kelvin. The reaction occurs from second to sixth phase, and we are supposed to use NRTL property method to simulate reactive distillation column. Okay, so okay, have you taken the screenshot of this problem? I'm just okay. First this slide.
Yes, sir.
Okay, and this slide. Okay, I hope you have taken it. Hope you have taken screenshot, snapshot. So let's move ahead. Okay, I will just close my Aspen actually. I don't need to save. I already have. Okay, so let's go to Aspen. Is there any discussions on reactive distillation column in sir's video?
Not up to now.
Okay. Okay, let's take this problem. This one was problem 3.7. Just give me a minute. I will open my problem from here. It's in chapter 4. As far as I remember, chapter 3. Actually. Okay, so this is the problem statement I have. Yes. So, okay. We have components of Hi, H2O, H2 and I2, right? So let's add everything. Hi, it has come as hydrogen iodide, then water, H2 and I2. Okay. Now we'll press next. The property method that we are supposed to use is NRTL as per problem. So I've chosen NRTL. I will press next. Okay. So we don't need to find any parameters. It's there. Now we will go to columns. We'll choose red flag model. It is reaction plus distillation. Okay. Let's open the problem diagram. So we are getting vapor stream, and so we need to have this line, top one. I will choose this one and this one. Okay. So according to question, align blocks. Okay. So this is F according to question diagram. This is D. This is B. And let's write something RD. RD. Okay. Now I will go to feed conditions. So we are told that temperature is 532.78 Kelvin. I will add 532.78 in units of Kelvin. Pressure is 22 bar absolute value. Guys, recording is on, right? Yeah, it is being recorded. Okay. Pressure is 22 bar absolute value. And okay. Okay, tell me one thing. Here feed flow rate is given LPH. So what should we choose here? It is liters per hour. So
So
what should we
liters per
choose?
hour.
So what should we
Sir,
choose
volume.
here?
Mass,
Volume.
volume,
It is
sorry, volume.
liters. It is liters per hour. And the value is 150 liters per hour. Okay. And we are given mole fractions. Okay, mole percentages are given. So we'll choose mole fraction. Mole fraction of Hi is 0.1. Water is 0.51. Maximum amount of water is present. Then H2 is 0. And iodine is already there. I2 is present from maybe some oxygen unit, that is 0.39. Okay. Now I will press next. So here, okay, it was told equilibrium based equilibrium limited reaction. Okay, number of stages were from problem it is 7. No, it is feed stage is 7. Number of stages are okay, total 8 number of stages, right? From problem. Here you can see it is total 8 stages. Okay, 8 stages. Condenser is partial condenser. And we won't play with this reboiler. Now we are given these two parameters, reflux ratio as 3.5. I will choose reflux ratio as 3.5 mole basis and other thing that is given to is D by F ratio, that is 0.55575. So we are supposed to choose D by F. It is D by F, right? It's D by F ratio. So distillate to feed ratio on mole basis is given to us as 0.55575. Please be careful with whatever is told here. It's mole basis, so we are choosing mole. If it's written in mass basis, you need to change from mole to mass. So just be careful while choosing this. Now we will go to stream. So feed is 7 above stage. I will choose 7 above stage. Now I'll press next. Okay, let's assume that everything is at same 22 bar absolute pressure only. Okay, so now can anyone tell me where will we add our reaction? How will we add our reaction? Because we have, this is just normal distillation problem that we did, but we need to add reaction. So how will we add reaction? Because we did not find any option here of reaction. Anyone?
I guess it's the left hand side of the panel.
Okay, how many we are here? Okay, this many students. Okay, let's go to as Harshil told here. So where did you see reaction?
Down
Here.
reaction. Yes.
So let's choose reactions, add
And
reaction, and this is just power law. The reaction is 2HI gives H2 plus I2. I will choose HI minus 2. Coefficient of HI is minus 2 gives H2 plus I2 here 1, 1. Okay, now we are told just a minute, it was somewhere mentioned. I just can't see that value. Okay, just a minute. I will just delete this first. I will delete this row. Okay, okay. I'm sorry, not here. I will go to. I'm sorry, I'm just deleting this. Okay, reaction, new. Okay, so here it is reactive distillation. We need to choose here react distillation because this is distillation plus reaction. So from type we need to choose this react dist. Okay, not power plant. It will take care of the model that we are choosing. This is kinetic slash equilibrium slash conversion reaction. Okay, in problem statement it was written that here equilibrium related limited reaction. So we'll choose equilibrium only and reaction number 1. Now we will add HI. So it will understand that this is the reaction is occurring in distillation unit plus I2. Here we will be adding 1, 1. Okay. So we have added this. Okay. And here we are not told what is the order of reaction or anything is not mentioned in the problem, right? So we'll just blank, we'll just leave this thing. Now I will press next. We need to add this reacting phase. It's a liquid phase reaction or vapor phase reaction. It's vapor phase reaction, right? So we need to choose vapor. Now, okay. So in problem, you can see that LNK is minus 0.03684 minus 2772.7729 by T. So we have this expression already there. So I will choose value of A as minus 0.03684 and value of B is minus 2772.7729. Okay, I guess it's done. Minus 2772. Okay, now it's done. I will press next. The concentration basis is partial pressure, right? Here you can see that K is in terms of partial pressure, P of H2, P of I2 divided by P square of HI. So here we need to choose concentration basis as partial pressure, correct? Now all inputs are done. So we'll just run this reaction. Okay, we forgot one thing to add. Can anyone tell what are we supposed to add? We have not added that thing yet. Anyone? Hello? Anyone? Are you guys following or not?
Sir, I just
Yes, sir, following.
Following, sir. Following.
Okay, what is something that is missing? What is something that we have not added according to problem statement? This is the thing that we have not added, right? In which stages reaction is occurring? So we need to add here from 2 to 6 as per problem statement. Okay, see, the reaction occurs from second to sixth stage. So 2 to 6 and which reaction? R1. Okay, now I will reset my simulation and run it. So yes, it is done. So let's go to results. Streams. So product stream, distillate stream. What is expected in distillate stream? Without knowing anything, what is expected in distillate stream? Maximum amount of H2 should be okay. H2 is minimum. Yeah, H2 should be minimum because it is a reactant. Maximum amount of water is there in the tops from distillate. H2 is minimum. So what does this mean? This means that reaction is occurring. H2 is being converted to HI. So we are getting 0.03709 of H2 and negligible amount of I2 in vapor distillate phase. And as expected, H2 should not be there in liquid phase then as it's a heavy lighter gas. So H2 is 0 in liquid phase and we are getting 0.1 of HI and 0.51 of we are getting almost 0 of both HI and H2 in liquid phase and maximum amount of iodine from water. So I guess this problem is clear. I am sure some of you may have faced the issue. Dhruv, were you able to solve or you face some issues?
Sir, yes, sir, just checking the results, sir.
Okay,
There
anyone
is
other
an
than
error that is being generated, sir.
okay, anyone other than him?
Can you show
can
the
you
results again?
Okay, see, this is bottoms and
and
this is distillate.
Yeah, I want to see. Thank you.
can you also show where you put that number of stage where reaction is taking place?
Okay, it was in this RD under reactions here. RD means reactive distillation block. Under that term, there is one thing reaction. So there I added starting stage
Okay,
2
okay.
to ending stage 6. Okay,
I think
anyone?
my
Okay, Dhruv, will you share your screen? What is the error that you are getting?
Sure, sir.
Okay, column not in mass balance. Okay, there are some calculations errors. Let's check all conditions. Go to RD unit. Input, yes. So 8 stages, partial vapor. Okay, these are correct. Now go to streams. Okay, this is also correct.
Can you go back again to the configuration?
Sorry. Okay, yeah.
Yeah, he has written the distillate rate, distillate to feed ratio.
Yeah, that is not, yes, that is not distillate rate. That is distillate by feed ratio. Distillate to feed ratio is given. Yes, I'm sorry, I could not notice. 0.555. Where did it go? 0.55575. Yes, now reset your simulation and run. Oh, it's done. Just check your mole fractions. Yeah, bottoms. Okay, those are not exactly matching, I guess. 0.924 is iodine in bottoms. Are you getting 0.924? No, you are not getting 0.92. Yeah, you are not getting iodine as 0.924 in bottom stream. You're right. So there is some
Yes, sir.
issue. Now check your reaction. Go to your reactions part. I guess it's some issue with reaction. Okay, click there. -2, 1, 1. That is correct. Now go to equilibrium. Yeah, here you may have made some mistake. Vapor, partial pressure A is 0.0 minus 0.03684 and B is -2772.7729. Okay, this is also correct. Strange. Go to that. Have you added the place where reaction is occurring?
Yes, sir.
Go to no, not there. Yeah, here under reactions. Reactions. Yes, it is 226 iodine. Yeah, this is also correct. Why are you not getting exact answers? Did you reset and run? Okay, we need to, I guess, check the feed conditions then.
No, sir, I'm still getting the same answer.
Go to your feed conditions once again. Is anyone? This is not mass fraction. This is mole fraction.
What is the correct answer?
I'm getting 0. Just give me a minute. I'm getting 0.92 iodine from bottom and from top.
Yes, sir. Got it. Got it.
From top 0.037 H2 and 0.857 water. Okay, so just be careful
Got it.
while.
Yes, sir.
Is just
The
be
silly
careful
mistakes
what.
I'm doing, sir.
Yes, yes. You just need to be careful what you are choosing. That's all. This is not something that you don't know. Okay, anyone other than him still facing issue, Samira?
So my Aspen is very slow.
Okay. And I don't know how to pronounce your name, but Vakas, I don't know if I'm pronouncing
Yeah,
it
yeah.
correct or not.
You're pronouncing it
Okay.
correctly. Yeah.
Sorry, did you solve it?
Yeah, yeah. I have solved it. Yeah.
Okay. Other than him, oh, Vaishnav is also here. Vaishnav, did you, or are you from somewhere else?
No, sir. Actually, I just came, so I
Okay, no
I
issues.
just had the question, the screenshot.
Okay, okay, then you will have to rewatch that video on YouTube if you want to. Okay, so before going to case study, let's complete this reaction part and let any one of you will share your screen and solve this problem. We are just comparing here models RPFR, RCSTR, R Stoic, and R Gibbs. So who wants to take this initiative? If anyone is not taking that, I will choose one. Hello, please, Dhruv, would you like to?
Yes, sir. Yes, sir.
Okay, then just say now you want to. Okay, I'll just show you the problem first. So in problem statement, okay, just take the screenshot. In problem statement, ethyl acetate is produced in esterification reaction. I guess everyone knows this
Sir, your
reaction.
screen is not being shared.
Oh, I'm sorry. I'm sorry. Okay. Now it's visible,
Yes,
right?
sir. Yes.
So we all know this reaction that is given in problem statement. Acetic acid plus ethyl alcohol gives ethyl acetate plus water. So the feed consists, this is esterification reaction, right? The feed mixture consisting of 52.5 mole% acetic acid, 45 mole% ethanol, and 2.5 mole% water enters our CSTR model with a flow rate of 400 kilomoles per hour at specified temperature and pressure. The reactor operates at 70 Celsius and 1 atm. Both the reactions are first order with respect to each of the reactants. So this is reversible reaction, right? It is told both the reaction. One forward reaction and one backward reaction. For these liquid phase reactions, one thing you need to note here, these are liquid phase reaction. Even if it's not told to you, you know that this is a liquid phase reaction. This is not vapor phase reaction, or this is not vapor liquid reaction. This is just liquid phase reaction. So for this, we are given kinetic data for the Arrhenius law, that is K and E values for forward reaction and backward reaction, and molarity is your basis. So perform Aspen simulation using non-random to liquid theory model, and reactor volume is given as 0.15 meter cube. Then we will be repeating this problem. Okay, here there is one issue. It's not RCST here. Here it should be RPFR. So we'll be repeating this problem for RPFR model and R stoic. Okay, so let's do one thing. First, let's do it with RPFR, then go to RCS. Okay, let's first do it with RCSTR, then go to RPFR, then R stoic and R Gibbs. Okay.
Can you show the
So,
last?
sorry, Vaishnav.
I wanted the screenshot, so can you show the last?
Okay, just do it. Let me know once you are done.
Yes, sir. Thank you, sir.
Okay, so Dhruv, are you willing to do it, or how
Sure,
many of
sir,
you are
I'll do it.
solving? Okay, how many of you are solving right now with me? With him, with Dhruv, how many of you are solving? Just let me know. I'm not going to. Vaishnav, you are doing okay. Your laptop is ready now. Okay, so let's do one thing. Dhruv, you start with RPFR model.
Okay, sir.
And everyone, please follow the process that he is following. So we'll just change the reactor type. Okay, Dhruv, first share your screen.
Is it
Okay.
visible, sir?
Yes, it is visible. Just give me a minute. Let me open the problem statement. Yes, it's here. Okay. So we are supposed to add acetic acid. Go to equals. It will be more convenient. You will not have to. Yes, acetic acid. Do it slowly. Then ethanol. Everyone should follow it. Ethanol. Just write ethanol. Okay, okay, it's fine. Ethyl alcohol. It won't show up, I guess. Okay, just write ethanol. Okay. Then ethyl acetate. Add and water. Yes. Just rename these four components for our convenience. Just write AA. Ethanol. EA. Just write EA for ethyl acetate. EA. Yes. Yes. Now press next. Okay, we are supposed to use NRTL model. So just go to NRTL model. Yes. Now press next. Yes. Just press run. Run. Just run it. Okay. Now let's go to simulation window and create our flow sheet. So here what you are supposed to do, just give me a minute. What you are supposed to do here, you are supposed to simulate one problem using four different reactor models, right? So Dhruv, can you first show your video?
Yes, sir, I was
Yes.
starting that.
Okay, do one thing. First go to, it is a reactor, okay? So let's go to first RPFR. Choose RPFR, yes. Okay. Now we are supposed to use some four different reactor models, and we will compare those four results in one time. So let's do one thing. Go to manipulator, yes, and choose duplicator. Yes. Okay. Now first add your stream in duplicator. So from here we can add different blocks. Okay. Yeah. Just do it. Yes.
Prasil, where to find this duplicator?
Duplicator is here in manipulators. Dhruv, just show it.
Manipulators and then
Yes.
second option.
Duplicator. Okay, let me ask one thing. What if let's say I'm telling that I want to. Okay, currently what is the flow rate? It is what is the okay? It is 400 kilomoles per hour. Let's say I'm told that I want to operate plant at some different flow rates, 1.1 times, 1.2 times, 1.3 times. So how should I proceed? What should I choose? I should choose some multiplier. So in multiplier, we will just multiply our flow rate with, let's say, 1.2, 1.3, 1.4. Okay. Okay. Now go to, yes. Okay. You save it first. So if it crashes, okay. Okay. Now, okay, I will tell you the inputs. Temperature is 75 degrees Celsius, 75 Celsius and 1.1 atmospheric pressure. And molar flow rate is 400 kilomoles per hour. Okay. Here choose mole fraction and acetic acid is 0.525 as per problem statement. Then 0.45 ethanol. 0.45 ethanol. Acetic acid, ethyl acetate is not there, and water is 0.025. Okay. Now press next. Okay. So what kind of reactor should we choose here? Reactor operates at 70 Celsius and 1 atmospheric pressure. So what should we choose here?
Specified temperature.
Yes, go for reactor with specified temperature. Okay, constant at
70.
70 degree Celsius. Okay, now press next. Okay, the length. Oh, we chose first RPFR. Okay, so okay, let's do one thing. We are told that volume is 0.15 meter cube. Okay, so let's assume that length of the reactor is 1 meter. So what will be the diameter for 0.15 meter cube? Just calculate it.
Sir, 0.15. No.
No,
Square.
0.15 is
Yes, sir.
volume. So volume will be equal to pi r square h. So it should be pi by 4 d square h. So volume is equal to volume is equal to pi by 4 d square h. We know the volume as 0.15, pi 4 constants, d we need to know, and h we are taking as 1 meter. So just calculate and tell what is the diameter. What should be the
What is
diameter?
the reactor
Yes,
temperature?
that is 70 degrees Celsius.
Okay.
Whoever calculate the diameter, let me know what is the value you are getting. I have calculated it.
So 0.2, I guess.
0.2.
2, I guess.
No, not 0.2. Just do the
What
math.
is
Pi by 4 d square h is equal to 0.15.
uh, 0.436.
Yeah, it is 0.4371. I'm getting 0.4371.
Yes, sir. 0.437.
Okay, just note diameter as 0.4371 meter. Okay, now What should we do? Yes. Okay. Read the problem statement. For this.
Second order.
Okay, second order. Okay, then. Okay, press next. If you think everything is correct.
Vapor only. Vapor only.
Yeah, it's a liquid phase reaction. So go just choose liquid only. Just be careful with these small things.
So where is
Let's
it
read
mentioned
again.
liquid?
Yeah, for next to overall second order, the statement for
For
this
liquid
liquid
phase, yes, sir.
phase
Okay.
reactions. We need to choose liquid. Anyway, esterification in liquid phase reaction. Liquid only. Do it slowly. Now go to reactions, add new. And this is a power law kind of reaction. Power law, press OK.
Sir, is it reversible or both the reactions are first order?
What does that mean?
Reversible.
Both the reactions.
Reversible,
It's a
yes, sir.
reversible. Okay, now press next. Okay. So acetic acid plus ethanol gives ethyl acetate plus water. This is reaction 1 with coefficient reactant side -1 and product side 1. Even
The
if I guess you
exponents
write,
was
just a minute, even if you write 1 at reactant side, just write acetic acid as 1. I guess it will
sir, it will
automatically
automatically get converted to
take
-1.
-1. Yes. Okay. And exponent, what is told? The reaction is first order with respect to reactants. So in reaction 1, what are our reactants? Acetic acid and ethanol. So we will just add 1 to both acetic acid and ethanol. Okay. Now press next. Now we need to add second reaction, right? Yes. Water plus ethanol gives acetic acid plus water plus ethyl acetate gives, yeah. Do it slowly, do it slowly. Everyone should follow it. Okay, now press next. Okay. What is the kinetics given for forward reaction? Yeah, it is liquid. K value is 2 into 10 is to 8. 2E8. Yes. And activation energy is given as 6 into 10 is to 7 joules per kilomole. 6 into 10 is to 7. Okay, now choose reaction 2. Reverse reaction. Value of K is 5 into 10 is to 7. 7. And value of E is 6 into 10 is to 7. Sorry, 6 into 10 is to 7. Okay, and basis is molarity for both the reactions.
Molarity, yes,
That
sir.
is what we have kept. Now you can run your simulation, right? Everything we have entered. Just run it and tell what are you getting.
Sir, in the feed of PFR in product is
Mass.
sir 112.
Go to mole fractions. Okay. You are getting 0.318 mole fractions of ethyl acetate. Water is 0.34.
And 0.
Okay. Anyone other than him who is solving? Did you get the same answers? Hello? Vaishnav?
Sir, I'm solving for CSTR.
Okay. So have you solved for PFR or you are starting with CSTR?
So this problem actually, the sir did it yesterday, sir. So he knew the answer.
Sorry?
So yesterday, the Sunday session, this problem was possibly done, I think.
Oh, okay. Okay. I didn't know this. So, okay, we have done PFR. Can you share your screen and show for CSTR, whatever you are doing?
It's not completed, so I'm doing it still.
Okay, so whoever who has not done, please volunteer who want to do it for our CSTR. Guys, please, or
Sir,
Dhruv will only solve it.
I can do
Sir,
it.
I did.
But
Yes.
I have not completed the PFR.
Okay, so are you facing any issues or
No, I was lagging behind.
sorry?
I was lagging behind. I was reading a question again and again.
Okay, so would you like to complete it and then want to go with CSTR model?
Yeah, I can do the CSTR. I can complete the PFR later.
Okay, for share your screen, don't close anything that you have done.
Okay.
Share your screen and video. Vaishnav, you will wait, you will solve R stoic and R gives. Okay.
Can you see my screen video?
Okay. Now, what is the noise?
Are you getting a noise? Is it the fan noise?
Okay. Okay, so here you just need to choose liquid. Okay, just add reaction because reaction will be here. Just choose liquid phase, liquid only. Just now go to reaction, add new.
It's a power
It's
law, right?
power law. Yes. We will be using reaction for next problem. Okay, just press OK.
It is acetic acid, ethyl
Yes.
alcohol, and it gives me ethyl acetate and it gives me water.
Acetic acid and ethanol. No. Reaction is acetic acid plus. Oh, sorry. You are right. You are right. You have written ethyl alcohol as EA. Okay.
Yeah.
Okay.
Specify another
Yes.
reaction.
Now add second reaction. Yes.
Ethyl acetate and water reacted. Acetic acid and ethyl acetate. Sorry.
Yes. Just write -1. Yes.
Do I have to specify the exponents here as well? 1 and 1?
Yes. It is told that reaction is first order with respect to reactants. So exponent will be 114 reactant in this case also. Yes. Now I guess we are done. So just run this simulation. Oh yeah, you are left with key. Okay, so for first reaction, no, it's liquid phase. It's not vapor phase. Yes. Joules per kilomole.
6 e raised to 7, right?
Yes, 6E7. Okay, now reaction 2. Add value of K as 5 into 10 raised to 7. And E is 6 into 10 raised to 7. 6E7. Okay, now you can run your simulation. I guess all inputs are done. Are you joining for first time or?
I'm joining for the first time.
Okay.
I started my course like after 3 weeks.
Okay. Just show your results.
Sir, it's a,
Yes, Vaishnav.
so what is the small n value? We should write 2, right? Second order.
Sorry, you are not audible. Can you repeat?
So what is the small n value? It's 2, right?
No, don't add anything because we are not told to add that T by T0 raised to N. So just leave it
Yes.
as it is. Okay, so what are
No,
you
but
getting?
we
Okay.
have been told that the reaction is, first order with respect to reactants, right?
Yes, so and no that okay. Wait, I'll show you. Can you go to the reactions?
You want me to go to the reactions?
Yes, R1. Yeah, here you can see that if T naught is specified, kinetic factor is equal to K into T by T naught raised to N. That N is not order of reaction. That N is that temperature dependence term T by T naught raised to N. So that is different from order of reaction. Okay. So we are not supposed to take N is equal to 2. In the previous LHHW model, I guess T0 was given and N was given. I'm not sure. Yes, in previous problem, T0 and N values were given. Okay, so it's done. So can you repeat this problem for RCSTR?
Yeah, I can.
Yeah. Now add just RCSTR. Vaishnav, is that clear? Okay. Guys, can you just give me a minute? I will be back.
So then I can solve it, right?
Sorry.
So then I can solve it.
Yes, yes. I will just be back. Just
Yes, please tell me if I'm wrong somewhere. Everything is specified. Has anyone solved it? So I can verify my answer.
Listen, I actually chose our law. Do you know how to convert it to
You'll have to delete it. You'll have to delete it and you have to solve it again. You cannot change the access. I don't know if you can.
you have to go back completely?
Yeah, yeah, you have to go back completely.
hello. Yes, it's done.
Yeah, yeah,
So what are you getting? CSTR is giving lesser amount of product than
yeah.
PFR. Is this expected?
Mm,
Is this expected for order of reaction 2? What if we have n is equal to 1?
then
Anyone?
we
What?
should get same result, right? If it is
Okay. Why?
that it
Okay, anyone? What if we have n is equal to 1? Dhruv, I don't know if you have studied this course or okay, yeah, you were studying CRE too. Dhruv, tell.
Yes, sir. Sir, n is equal to for n is equal to 1 and 2, sir. It is, sir. I cannot can't figure it
Okay.
out, sir. Sorry, sir.
Okay, you
Sir,
guys need to. Okay, who is?
this is
Yeah,
Vamsi.
say forms. Yes.
Actually, first order reaction is more faster than second order reaction.
So,
So that's why whatever the result is coming, that is justified, I think.
no. In first order reaction, if you find that expression for RCSTR and RPFR, it's there in Fogler, I guess. So you will see that both the expressions are same. You are getting same. Those are not actually same, but you are getting same expression for both CSTR and PFR. So for CSTR and PFR, when we are using n is equal to 1, it should be same. And for any reactions where n is greater than 1, the conversion using PFR will be more than conversion using CSTR. I guess this thing is shown in Fogler. Okay, so be careful. You should keep this in mind. When n is equal to 1, you will get same conversion for both plug flow reactor and continuous reactor. and for n is greater than 1, PFR should be more than CHTR. Okay, so this is what we are also getting.
Yes, sir.
Ethyl acetate is more in PFR than CHTR. Okay, so
Yeah.
now third is R stoic and R Gibbs. Who wants to do it? Vaishnav, can you?
Sir, 1 second. Then I will have to log in from my PC.
Okay.
We have to do it now using RPlug, right?
Sorry, R stoic
We
and
have
R
to,
Gibbs. Anyone who started solving? Dhruv, did you start?
Yes, sir. I'm doing for R stoic right now.
Okay, do it for R stoic and R Gibbs. Everyone just do it. Uh, Whenever Vaishnav is able to share, we will see how to do it. I guess you know how to do it.
Sir, am I visible?
Your screen is visible. You are not visible.
No, it's okay. 1 second.
No. Uh, why are you having two? Okay, okay, let's do it. Let's do it. Okay, let's start with R stoic and R Gibbs. Okay, R CHTR only you have done it.
No, sir. Actually, I selected power law and I did some mistake, sir. That was the thing.
Okay, so you want to repeat? Okay, let's correct that first. Okay, cut it. I will suggest you to use one multiplier so we can do both R stoic and R Gibbs in one seat.
Okay, sir, I think so I need to go on. So what shall I do? What shall I select?
Just press this double arrow. No, 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 no. Just close this. Just close this. Remove reaction one. Yeah, now just press that double arrow and choose reaction R1.
Remove this. So,
Okay, then go to reactions on left screen. You can see reactions R1. Just delete that R1.
no, it's not happening. I don't know why. There's no cut option.
Sorry. No, no, no.
Uh,
On left side, blocks, then sensors, utilities, reactions. In left window, you can see. Not here.
okay,
Reactions is
sir.
there. Yeah, just delete that.
Okay, this is the new one, sir.
Yes, delete this yarn and now add new reaction. Go to
Yes, sir.
new
Selected.
power law.
Okay.
Yours,
Select
you are
next.
lagging. You are lagging. Okay. Press next and add reaction conditions. What is acetic acid plus ethanol?
Use water plus ethyl acetate and
Yes, that is reaction one. Yes, add -1, -1, 1, 1 on product side and exponent 1, 1 for reactants. You need to add exponent, order of reaction. 1, 1 for reactant. It is told. Reactant is first order with respect to each reactant. Now add second reaction. That is reverse. This is reversible reaction. So you need to add second reaction. Water plus ethyl acetate. -1, -1. Exponent should be 1, 1.
Okay, sir.
Ethanol, yes. 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 Yeah, now you are done. You need to add just kinetic parameters. Yeah. K is
Yeah.
K
One,
is 2
one
into
second.
10 raised to 8. 2 into 10 raised to 8. And E is 6 into 10 raised to 7 joules per kilomole.
And this is
Now go to reaction 2. Those all terms we don't need to specify. Yes. Now add K is 5 into 10 raised to 7. And 6 into 10 raised to 7.
yes, sir.
Now
I did
reset
the
and
same.
run. Sorry.
Actually, did the same thing.
Okay, let's see what are you
Yes.
getting. And let's find out what is the issue.
It's there. Sorry. Actually, I
Go
think
to
so. I
mole.
solved the right.
Go to mole fractions. Yes. Oh, you are not getting. So I guess the issue is in phase you have chosen. Go to reactor, CSTR, and just see what phase you have chosen. I guess you have chosen vapor phase only.
I chose liquid phases.
Just so it this should not happen then.
Oh, sorry.
Go to CSTR block. I can't see.
No, no, I actually reinstalled the CST. Sorry. Then
Yes,
now it will.
that's fine. Now reset and run it. Okay. Just show the results.
No, actually, I reset the this
It's fine. It's
block. So
fine. Just show it.
yes,
Mole
sir.
fractions. You're getting it right.
Sir.
Yes, you're getting. No, your answers are not matching.
Sir, I'm done
No,
with
no.
all.
Just give us a minute. Your answers are not
Oh,
matching. Just so, just do it slowly. First, show the reactor. There is some issue in reactor conditions only, not anywhere else.
Uh,
Go to reactor.
kinetics.
No, go to reactor. Go to reactor. These things are fine, I guess. Go to reactor.
Fine.
RCSTR block. Just go there. Do it slowly.
Yes, sir.
Yeah, pressure is 1 atmosphere. What have you chosen this thing?
1.1 atmosphere. It was 75 degrees Celsius. Sir. No, it's 70 only. No?
70 and 1 atmospheric pressure and 70, and your volume is 0.15 meter cube.
That's 150 liter. No?
Okay. Uh, Go to kinetics here. I can't figure out what's the mistake. Go to kinetics. Yeah, you have chosen correct reaction. Just show me the feed conditions. I guess it won't matter.
It's the same.
Mole fractions. Okay. No, it is 0.45 ethanol, not ethyl acetate.
Sorry.
Yeah, no, that's fine. 0.45 ethanol. Yes. Now run it. Reset and run.
Yes, sir.
Just be careful when you are solving the problem. These are silly mistakes. Now
Yes,
check
sir.
what are
Now
the.
the conversions are right. Appropriate. Yes, sir. The conversions are right. Sir. So,
Okay, yeah, now it's correct. Okay, Dhruv, did you solve it?
Yes, sir.
Can you share your screen? Vaishnav, just let him show. Okay, so with R stoic, can you just show us all inputs so everyone can follow? Just go to inputs of R stoic first. Yeah, just go to R stoic. Yes. Click on R stoic block. Yes. So in R stoic block, we are told 80% conversion of ethyl alcohol. So what he has done, he has chosen 0.8 and fractional conversion of component ethanol, and reaction is acetic acid plus ethanol gives EA plus water. So this is correct. And for R gives 1 atmospheric 70 degrees Celsius. And what have you chosen? Phase equilibrium and chemical equilibrium. Okay. Okay, so I guess we are
I
done.
guess this.
No,
Yes,
no,
sir.
no. Calculate phase equilibrium and chemical equilibrium. You are correct. So let's go to results part and see. In our product CSTR, product Gibbs, product R stoic, and product PFR, where are we getting maximum conversion? Where are we getting
Sir,
maximum value of
Gibbs.
ethyl acetate? Okay,
Sir,
ethyl
Gibbs.
acetate is given 0.43 and followed by R stoic 0.36. Then RPFR and RCSTR. R stoic is based on just conversion value that we are giving and it is just calculating. So R gives is 0.43. So that is we can't get more than 0.43 and that is what we are also getting. RPFR is 0.318. So we are not getting anything more than 0.43. Okay, I guess it's clear to everyone. Please respond.
Yes, sir.
Okay, so let's take the case study now, or just give me a minute. Okay, so till now, yes, okay. Dhruv, I am getting I'm getting 0.337. Okay,
Or
wait,
sir,
I will share my screen. Just a minute, I'll share my screen. Okay, so with P1 is my CSTR, PFR, Gibbs and Stoic. So with P1 CSTR, I am getting 0.30. That is correct. With PFR, I'm getting 0.31. With R Gibbs, I'm getting 0.377, not 0.43. So this is the condition, calculate phase equilibrium and chemical equilibrium. And pressure is 1 atmospheric and temperature is 70 degrees Celsius.
I am getting the same 0.43 with RPs.
Sorry.
I am getting the same 0.43 with RGIPs.
Okay, so I guess I made some mistake. 70 degrees Celsius and 1.1 atmospheric pressure, that is correct. Okay, so can anyone tell me what is wrong? You have chosen this option only, right? Calculate phase equilibrium as well as chemical equilibrium.
yes, sir.
Yes.
And it is 70 degrees Celsius and 1 atmospheric pressure, right?
Yes.
Nothing other than this.
Yes, sir.
No, nothing other than this.
This is strange. I don't know why I am getting this answer.
Can you reset the simulation and run it once again?
So maybe there could be issue in the feed, I guess.
No, all other answers are correct, and I am taking feed from this duplicated stream only. So it should not be an issue. Streams. Yeah, I'm getting 0.37 only.
Sir, F3 only once you could check, sir.
F3, okay. Yeah, that is correct. 0.525, 5.45, 0.025.
These values are correct, sir.
Yes.
For me, the include vapor phase option is correct. Tick. It is selected.
No, you should not, because this is a liquid phase reaction, right?
Okay, sir.
It is clearly mentioned it's a liquid phase reaction, so you should not add. Yeah, there should not be huge difference between all these. So 0.37 is reasonable value. Now, just change it to just untick that
Sir, yes,
option.
sir. The value changed, sir. Now it is the same as
0.377.
0.377 and 0.40.
0.40
Yes, sir.
watt. Yeah, correct. Just be
Yes.
careful. These are very small
Okay.
mistakes. Okay, so now let's do our final problem of today's session. That is distillation column, case study 1. So wait, let me just open my problem in the book. I'm more comfortable with book. So okay, I will read out the problem. So the problem is a hydrocarbon stream H is supplied at 5 degrees Celsius and 2.5 atmospheric pressure. The pump P1 discharges the feed F at 10 atmospheric pressure. In table, the component-wise flow rates are tabulated for stream H. The schematic representation of the complete process integrated with pump and 5 DSTW column models is shown. So this is our problem. So these are the flow rates of C2 is ethane, propane, isobutane, N-butane, isopentane, N-pentane, and hexane. We are given flow rate of all streams. This H stream, this is the H stream that is passed to the pump and then fed to 1, 2, 3, 4, 5 distillation units. So for these 5 distillation units, we are given condenser and reboiler pressures. Each distillation column has total 20 stages, including condenser and reboiler. For the light key and heavy key, we expect 0.999 and 0.1% recovery in each distillation column. Use Peng-Robinson equation of state to simulate distillation train and report the composition of distillation products. Okay, so I will show you how to solve this problem. Okay, so can anyone tell me what will happen without seeing anything? We are having C2, C3, C4, C5 and C6. We are adding it in the first column. So what will we get from top? What should we get from top of the first column?
C2, C3,
Sorry.
C2 and C3 components.
Yes, majority in C2
Yeah.
and bottom C3. Then in this
What
next column,
like we'll get
bottom in mixture of all these.
yeah, and next we'll get C3, maybe some C4, N C4.
Yes. Okay, let's solve this problem. I will show you how to solve it. Just pay attention. Do you want to close the current? Yes. Is actually there are no changes. Okay, let's add our components first. Okay, have you taken screenshot? Just do it. I will wait for 20 seconds. One.
Yes, sir. Done.
Now this. Done. Done or not? Okay, I assume it's done.
Yes, sir, done.
Okay. Okay, so let's add first components. So we have C2, that is ethane, C3, that is propane, IC4, that is isobutane. I guess isobutane won't be here. I will have to find isobutane, isobutane, then just butane, then isopentane, then just pentane, and we have hexane. Okay, so it's done. Let's rename it according to our problem. So it's IC2, C3, IC4. So just rename it like that. C2, rename. C3, rename. IC4, rename. NC4, IC5. Are you guys following?
Yes, sir.
Yes, yes.
And NC6. Okay. So we have chosen these components. Now I will press next, and we are told to use. Here you can see it is told using the Pang-Robinson property method. So we will use Pang-Robinson equation of state. So Pang-Robinson. I will just press next. I will just run it. So we have parameters ready. Now we need to add our flow sheet. So let's, without doing anything, without thinking anything, let's first create this flow sheet. So we have one pump and then 1, 2, 3, 4, 5 distillation units. So we will add first pump. Where should be pump? In pressure changers. So first we will add a pump. Then okay, here it is told that 5 DSTWU column models, right? So I will choose. I will go to separator. Sorry. Yeah, I will go to column. I will add 1, 2, 3, 4, and 5. Okay. And then, okay. This is our feed stream. And this is going to here. This is distillate 1. I'm just doing it as per flow sheet that is given to us in problem, right? Okay. So flow sheet is ready. Now let's rename everything as it is told. So this one is H. Okay, let's rename this P1 and C1 to C5. Okay, so this is P1 and this is C1, C2, C3, C4, and C5. Now this one is our H stream that is added to the pump. This one is feed. Okay, this is H, F, then D1, B1, D2, B2, D3, B3, D4, B4, D5, B5. So B1, B1, B2, B2, D3, B3, and here D4, B4, and D5, B5. Okay, I will wait here. Whoever who is solving with me, Dhruv is doing, Vaishnav, I assume you are doing.
I am, but can you wait? I'm reading
Yes,
it.
yes, I will wait. I will wait. That's why I asked. Okay, so who was saying this? I'm sorry, I could not recognize voice.
I am saying
Okay, okay. Dhruv, did you?
I'm starting now, sir. I had gone out of the room for a minute.
Okay, and Vaishnav?
Yes, sir. Yes, sir. 1 minute. I'm
Okay,
just.
wait, I will open this sheet so you can. Okay, just complete it and let me know. Then I will move ahead.
Yeah, I have completed it. I had a doubt.
Yes, please ask. Who is this? Can you tell
I
your
am
name? Okay, yeah.
Aspen.
Sorry. Yes.
Since we
I
are,
will familiar with your voice, I guess, by next session.
no problem, no problem. I
Okay.
had a question that
Yes.
since we are modeling, you can say that we are modeling 5 blocks all together. So
Yes.
won't there be a problem while simulating it?
No, it won't be a problem. Why it will be a problem?
Because I think the case study one that sir performed, I tried modeling it all together. I think there
Okay.
were 6 or 7 blocks together, and I was unable to perform the simulation because it was showing some error. But when I modeled it alone, by taking each blocks and then simulating it, then I got my answer.
Okay. So, what was the problem? What was the
Uh,
problem statement? I don't remember it.
the problem I was, oh, the case study, I don't remember it as well.
Okay.
Yeah.
So, can you write me? I will solve it for you and I will share that Aspen file with
No,
you.
no. I solved it. I simulated it by simulating each block while completing it. Like I modeled P1, I ran it, and then I added C1, then I ran it, then I added C2 and ran it.
Okay, but it should work like this. It may be some issue in. It should work like
Oh,
this.
I was using a separator, if I remember properly, and it was not unable to separate it according to the mole fraction. According to the fraction I needed it to.
Okay. Wait, tell me, which can you tell me, or just when you are writing me an email, just mention this, in which week this problem is solved, and can you just mention it? I will try with solving whole unit at once, and I will let you know.
Okay. I think I have. I think I have the saved file. I'll mail it to you.
Yeah, just
I
do
can.
it, and I can check what is the error that you are
Okay.
getting.
Okay. Thank you.
Ideally, what we should do, yes, it's okay. Ideally,
Yes.
what should happen? We should first simulate this. If this simulation is correct, we should go ahead in plant, not here in plant. We should first simulate this separate section, and we should match our product quality with actual value. Then we should go here, repeat the problem, go here, go here, go here. Okay, I have a quick question. Why should we use 5 distillation columns? C1 is saying the ethanizer, D2 is saying the propanizer, C3 is de-isobutanizer, D4 is butanizer, and C5 is de-isopentanizer. So why do we need 5 distillation columns? Can we do it with one column?
Yeah, we can, but the column
So
will
we
be
we
very
need a
big,
multi-stage.
and the purity would not be as good as the 5 different distillation columns.
Okay, I'm just stopping you. Yes, Vaishnav, say.
Also, we can use the multi-fraction distillation column for this.
Okay, multi-fraction column. Okay, Vaishnav, you are saying something.
Same thing, sir. Multi-fraction column. That's what.
Yes, we can't do it with one normal distillation column because this is the thumb rule. If we want to separate n components, we should have n minus one distillation columns. Ideally, we should have n minus one distillation column to separate each of the component. So here we have one column. Here we will be getting ethane, propane, isobutane, butane, isopentane, and pentane. We are not separating hexane because hexane is only 5 kilomoles per hour. We can use even one more column for hexane, but that is meaningless because hexane has only 5 kilomoles per hour flow rate. So it will be, I guess, here mixture of pentane and hexane, and it will be okay because it's only 5 kilomoles per hour. Okay, so this is the thumb rule. If you have n columns, if you have n components, you should have n minus one distillation columns in series, or in this kind of train you need n minus one columns. Okay, so should I move ahead? Is everyone done with this flow sheet? Guys,
Yeah, I'm done with it.
okay, Dhruv, Vaishnav, should I move ahead?
Yes, sir.
Yes, sir.
Sir, could you just, sir, when the feed H, the statement in the first part is a
Yes.
hydrocarbon stream H is supplied. So, sir, the components will be the one mentioned C2, C3, I, C4. These will be the
In
components, right, sir?
H. In H, yes,
Yes, sir.
here. We will be
Okay.
giving that condition here. Okay, so let's give the
Oh,
condition. So according to problem, okay, I'm reading this problem from book only, so you can check screenshot. So it is 5 degrees Celsius and 2.5 atmospheric pressure with uh, okay, flow rate is not given, so let's just add flow rate is given, I guess, or not.
We have different specific flow rates of all the components.
Yes. We have different flow rates. Yes, so we will go mole flow. It is in mole flow with kilomoles per hour. So C2 is 35, C3 is 50, isobutane is C130, N-butane is 200, isobentane is 180, N-pentane is 200, and this N-hexane is 5. Okay, so I'm waiting. Okay, have you done it? Let's do it slowly.
Yeah.
What's the mole flow rate?
Yes, we don't need to mention it because it will just take the summation. 800. We just don't need to mention this thing here. If we are mentioning mole fraction, then we need to give mole flow. Okay, I am going ahead now.
One finish the previous.
Yes, please. Okay, I'll wait. I will keep this open. So these are the feed conditions. Let me know.
yes, sir.
Okay, so let's move ahead. The next section is pump. So it is written that the pump P1 discharges the feed F at 10 atmospheric pressure. So it is pump and discharge pressure is 10 atmospheric pressure. Okay, and we are not given any efficiencies here, so it will take automatically 100%. Okay, if we are given efficiencies, we can add these values here. Okay, we are not adding because it's not given in the problem. These things also suction area. If it is given, just add it. If it's not given, just leave it. Okay, so we are done with pump. We just need to add discharge pressure and we did it. Now let's go to first column, that is de-ethanizer. So in de-ethanizer, okay, what is written? Uh, each distillation model has total 20 theoretical stages. So in each column we have 20 stages. So just add 20 here And condenser and reboiler pressure, you can see it's given here. In de-ethanizer, it is 9 atmospheric pressure. So both have 9 atmospheric. So I will add 9 atmospheric, and here also atmospheric. Okay. Now what is told? We expect 99% and 0.1% recovery of light key and heavy key respectively in each column. C. We, for the light key and heavy key, we expect 99.9 and 0.1% recovery respectively. So let's add this. Component C2, that is light key, that should be 0.999, and heavy should be first C3. So it should be 0.001. Is this clear?
Yes, sir.
We will not add hexane here, okay? Because from first column, we need maximum amount of, and it will be ideally maximum amount of propane. Okay, so we will add it. Okay, I just want to show one thing. So I will just deactivate all these things. I hope it will work. I don't want to delete it. Deactivate. Deactivate. No, it won't work. Just give me a minute. Okay. No, it won't work. Okay. I just want to show that from column one, then the way that one student was saying, if we individually simulate it. So if we are individually simulating it, so we will be getting maximum amount of heavy maximum amount of pentane, propane, butane, all in bottom. So let's first complete whole sheet and then run our simulation. I can't deactivate it. Okay, so this is done. Now we will go to second column. Same thing, 20 number of stages, and pressure is 5 and 5 atmospheric in both reboiler and condenser. So it is 5 atmospheric pressure in reboiler and condenser. Here also, now what will be our major product? Propane. From top, that is depropanizer unit. So from top we should get 0.999 recovery of propane, and heavy is isobutane, that we should get 0.001. Okay. Are you following, guys?
Yeah.
Yes, sir.
Correct.
Yes. This was depropanizer. Now we will go to de-isobutanizer. So here also 20 number of stages, and pressure conditions are 4 and 4. So we will add 4 atmosphere here, 4 atmosphere here. Here also 0.999 recovery of isobutane. Sorry. Okay, this is done. C3 column. Now same for sheet 4. 20 pressure conditions are 3 3 3 3 atmosphere. This is debutanizer. So we will get maximum N butane 0.999 and IC5. Okay, now our last column C5. That is also 20 stages with 2 and 2 atmospheric pressure. Here also this is the isopentanizer. So here we should get 0.999 and 0.001. Okay, is this flow sheet clear to everyone? Have you guys completed input? I'm just running the simulation now.
Can you Show me the inputs for C4.
C4. Okay, so it is this.
And C4 and IC5.
It is debutanizer. So from top we should get maximum butane. So light key is N-butane of 0.999 and heavy key is isopentane. That is 0.001. And then C5, that is de-isopentanizer. So 0.999 of isopentane and 0.001 of N-pentane with this condenser reboiler condition.
Thank you.
Okay, so my simulation is ready. I have completed it. So let's see what are we getting. So D1, D2, D3, D4, D5. Okay, we will be seeing these 5 columns. So from D1, we should ideally get maximum amount of propane. Sorry, maximum amount of ethane. And that we are getting. Okay. Then in D2, okay. Now we can see that in B1, there are propane, isobutane, butane, and isopentane, N-pentane, and hexane. And C2 is negligible. Okay. Now this B2 stream, okay, let me show you the flow sheet. This B1 stream that has maximum amount of these heavy components. Where did it go? Yeah. This B1 stream that has maximum amount of these heavy components. That is sent to C2 column, that is depropanizer. So from depropanizer on the top, we are getting D2, that is D2 column. We are getting maximum amount of propane, that is 0.996. And from bottom, we should ideally get a mixture of these IC4, NC4, and these all heavy components. Now, this B2 stream, now we want to separate IC4. So this B2 stream is sent to deisobutanizer, and from the top, we are getting 99% of isobutane. And bottom, we are getting these 4 components in majority. Now, this B3 is now sent to this column, debutanizer. So from there, we are getting maximum amount of butane. And from that column's bottom, we are getting maximum amount of isopentane, N-pentane, and N-hexane. And that is sent to our last column. So from there, we are getting 99% isopentane. And from bottom, 97% normal pentane. Okay, we don't need to, we can add one separate column to separate these two also, but it won't make any sense because already the quantity is very less, 0.024. So if you want to do it, we can do it. Okay, so is this problem clear to everyone? Anyone who is not able to solve?
Yes, sir, I have solved, sir.
Okay, you solved and your answers are matched, right?
Sir, kind of similarly have them matched, sir.
Okay, anyone other than him, Vaishnav, did you?
Sorry, sir. It's matching.
Very good. And Vakas?
Yes,
Sir,
the
in the
similar
B's
answer.
bottom stream, you are showing that the like sir,
Yes,
could you
Dhruv.
show your bottom stream once?
Okay. Did you guys understand the concept? Forget this
Sir,
problem.
the
Okay.
results of bottom
Okay.
stream.
Let me show the result first. Okay. B1. Which stream? Okay. Which stream?
Yes, sir. Sir, the values are a little different for me.
Have you correctly added these values? 9 atmosphere and these things you
Yes,
correctly
sir.
added, right?
Yes, sir.
Okay. I don't know. Maybe it's some when you use Peng-Robinson property
I'll check it
method.
again, sir.
Okay, it's not a big deal actually, but you are able to solve. So let's first forget this problem that we simulated this thing. Just think as an process engineer, you have mixture of these many hydrocarbons. So you want to separate them individually. So what will you do? You have 5 or 6 components in a series. So what will you do? You will perform something like this. If you are not going for some the way the as you are told you all told you should use multi-fractional column, that is correct. But if you don't have that option, what will you do? You will do this kind of thing. You should think logically, right? That first I should separate ethane, then bottoms I should send to next column, and from there I should separate propane, and like that. Okay, so this was DSTWU model, right? So from here, what will we be getting? We will be getting minimum number of stages. Okay, so here we are getting our separation in 11 stages only, and reflux ratio is 1.05. So what can you do next now? We'll not be doing it right now, but what can you do now next? You have designed
Sir, use a
DSTWU.
radfrac model and
No. We can use
sir,
a distilled
replace
block.
the DSTWs with radfrac model, sir.
Yes, we
Replace
will.
it with distill, right? First,
Uh,
we replace it
hmm,
by distill and then we replace it by red flag, right?
no, you can directly go to red flag
Believe-
because you have all parameters required. You have this minimum number of stages, the values that you need to add. So what do you need to add? You need feed stage, that is 10.09, that is 10. Then you need this distillate to feed fraction, D by F ratio you need, and you need this minimum, you need this actual reflux ratio. You need these three inputs. Okay, let me show you. Let's say I have this red frac unit. I'm adding red frac here. So what are the inputs that you require? You require number of stages that we have from here. Okay, we have actual number of stages. Then we have this D by F ratio we have, distillate to feed ratio. No, that is distillate to feed fraction. That is not ratio. You can use this reboiler or condenser. Reboiler duty you can use. So here, from here, you can add reboiler duty or condenser duty, and you can add reflux ratio. Then from stream section, you can here add the feed stream location. So in when you are doing this, what I was saying, when you are solving this red flag column, what you should ideally do, you should first simulate this C1 column only. Till here you should simulate, and then whatever you are getting, then you should go here. One by one you should do it, okay? When you are doing red flag. You can also do it in one all in once, but do it one by one. Will you do it, or you know how to do it, right?
Yeah, we know how to do it. Yeah.
Okay, so just solve it, and if you are yes. Uh, hello.
Sir, can I share my screen once?
Yes, please do it.
Sir, for in your case, sir, this value it is coming highest, and then there is a table like for in first case the bottom of isobutane is highest. This for me it is not the case, sir.
Okay, just show me all conditions. I guess there is some issue. I'm not getting 0.96 and hexane. This is column number 1.
1.
0.999, 0.00. Okay, now go to column 2.
Column 2, sir.
Column 2 is at 5 pressure, 5 atmospheric pressure. Condenser
Yes, sir.
is okay. Yeah, it's 5. Sorry, it's 5. Propane and isobutane. Okay, now go to C3. That is 4 atmospheric pressure, 20, 0.999, 0.00. Okay, correct. Now go to C4. That is 3 atmospheric and butane and isobutane, and this is also correct. Now go to C5. 2 atmospheric. Okay. Now go to your feed condition. No, not there. H,
He has done,
stream H.
wait, one second, please. He has done something wrong. He has done N pentane. His heavy component is hello.
Okay, yes. So your C5 column.
C5
Yes,
column.
yes, C5 column. Yeah, here it should be isohexane, isopentane, not n-hexane. Bottom. Yes,
Heavy key.
isopentane. Yeah, isopentane and n-pentane. It should be isopentane in light key and n-pentane in heavy key. Wait. I'm sorry. Just a minute.
Sorry,
This
it is
d-isopentane is yeah. Yeah,
isopentane
here.
and N hexane.
Yeah. On top it should be diiso. Sorry, on light key it should be isopentane. Yes, and
And
in
bottom
bottom
N
it
pentane.
should be n-pentane. Okay.
Yes, sir.
Now run it and check all
Sir,
other.
it was this only initially, I guess.
Okay, now check your results of B1, B2, B3, B4, B5. Okay, but your other just give me a minute. I will just check it with my answers. Just keep your screen as it is. So in B1 it is 0.16998. Yeah, it's matching. 0.181. 0.2. Yeah, it is matching. You are right.
Okay, sir.
It's
Okay.
done.
Then it's correct. Okay.
Yeah. 0.97 from. Yeah, that is correct. Okay. So are you guys having any trouble with this problem? I guess it's done. So in next week, what we'll do, we'll be solving this one plant, that is vinyl chloride monomer production unit. So it has reactors, that it has pumps, it has heat exchangers, it has two distillation columns. So that is a more complex problem. So we will solve vinyl chloride monomer production unit in next week, and then we will solve this one more problem of petroleum column that has compressor, and it has mixture of benzene, pentane, toluene, octane, xylenes. I guess there are 10 to 15 components in feed. We will solve that problem. Okay, this will we will do it for next week. So next week is Holi. So I assume will you guys join or not? I guess we won't play Holi in night. Hello?
Sir, don't know, sir.
So you are going to play in night?
No, sir.
So
I cannot.
next day, can you please put the meeting in the next day
Tuesday.
Yes,
after Holi?
yes, sir.
Actually, I'm going.
Wait
I'm
on.
also going. Yeah. See,
Can you do the same on Saturdays? Because
Saturday is not possible because I'm going home. I'm traveling on Friday. I will be home on Saturday, Sunday, Monday. Monday I am also at home, but I will be taking session. But okay, what do you guys suggest? Should we do it on Tuesday?
Sir, anything works for me. I'll be traveling on this Friday, Saturday.
Okay, where are you coming? You are coming to Mumbai.
I'm coming to Mumbai.
Oh, you are coming to Mumbai, and we are going. We are running away from Mumbai.
I'll be there for 1 week, sir.
Oh, great. Where are you staying in Mumbai?
Sir, Mumbai Central.
Wait, let me stop the recording. Then we can have these chit chats.
sir, he won't attend.